We have finally reached Newton's third and final law in section 4.6. Our objectives here are to relate forces through an understanding of Newton's third law and be able to identify third law force pairs in various circumstances. Newton's third law essentially addresses the fact that forces are always interactions between two objects. Basically, what we're saying is that if one object pushes on another, that second object will always push back with equal magnitude but in an opposite direction. Our equation to relate that is to say that the force by object 1 on object 2 is equal to, but in the opposite direction, of the force exerted by object 2 on object 1. Think about it as maybe pushing your hand against your desk. However hard you push against your desk is going to push back on you with the exact same amount of force, but in the opposite direction. Really, this means that forces will always occur in pairs. A single isolated force cannot, in fact, exist. The force that object exerts on any other object is going to be called that action force, and the second reaction force is the one that's kind of pushing back in the opposite direction. It doesn't matter which force you call the action force and which one you call the reaction force. The idea is that you always have this pair of forces where if one object is interacting with a force on another, that second object will always push back with the same amount of force in an opposite direction. So, for your notes, Newton's third law says that the action force is equal in magnitude and opposite in direction to the reaction force. A couple of hints to help you identify third law pairs. There are very common misconceptions or mistakes that students make as they're trying to identify third law pairs. So hint number 1, remember this. Third law pairs act on different objects but are always of the same type of force. So in the example of you pushing on your desk, it's the same kind of contact force, a contact force of touch between your hand and the desk, and that's the same type of force in each one, but they're on different objects. One force was your hand pushing on the desk, and the other one was the desk pushing on your hand. So different objects but the same kind of force. Hint number 2 is that third law force pairs will never ever end up in the same free body diagram. I could draw a free body diagram of my hand and show the force of the desk pushing on it, or I could draw a free body diagram of the desk and show the force of the hand pushing on it. In either case, those free body diagrams would be two different diagrams, one for the hand and one for the desk. Be careful about differentiating between third law pairs and the idea of labeling all the forces on a single object with that free body diagram. Third law pairs will always be in two separate diagrams. If you remember these two things, they will definitely help you in identifying third law pairs. So let's look at a couple of examples to show you what we mean by these third law pairs. Let's say that you have a hammer that is hitting a nail. We'll see if I can draw a hammer here. So there's your hammer, here's the nail. If we looked at the forces and the interaction here, we could certainly say that the hammer is exerting a force on the nail. We'll draw the hammer's forces in green. So hammer is pushing down on the nail. Now, as this hammer is in contact with the nail is also going to be exerting a force on the hammer. If there's contact between hammer and nail, the nail is also going to be pushing up. So there's the force of the nail. These would be considered third law pairs. The force that the hammer exerts on the nail is exactly equal to, but in the opposite direction, of the force that the nail exerts on the hammer. If we were to draw free body diagrams of each object, we could draw a free body diagram of the hammer itself and show that the hammer has the force of the nail pushing up on it as it is in contact. And we could draw a separate free body diagram of the nail and show the force of the hammer pushing down on it. In another example, we could look at a computer sitting on a desk. As this computer is sitting on the desk, we know that the computer pushes down on the desk. Basically, the weight of this computer is going to be pressing down on the surface of the desk. The desk is also going to have to respond to this. The desk will push up with just as much force on the computer as the computer pushes down on it. So the free body diagram of the computer, if we were to diagram out all the forces acting on this computer, the computer has its own weight from gravity, and it also has the force of the desk pushing up on it. This force and this force are the exact same thing. When we're identifying third law pairs, though, we'd have to diagram out a second diagram of the desk itself. The desk also has its own weight, so there'd be the force of gravity on it. The desk has normal forces pushing up from the legs, holding it upward, and the desk also has the force of the computer pressing down on it. So the computer force here and here would be the exact same forces, but these two would now be considered third law pairs. The force that the computer pushes down on the desk with would be equal and opposite to the force that the desk pushes up on the computer with. Let's look at one more example that tends to be confusing for students. What if the desk wasn't there? What if the computer instead was just in free fall? What third law pairs would we be able to identify in that type of scenario? Let's draw out a diagram and we'll see if you are able to come up with the correct answer. In this case, we now have the computer that's simply in free fall. So here's our computer, and the computer is going to be free falling towards the surface of the earth. Here's the earth down here. As the computer falls towards the earth, there's obviously a force acting on it that's causing it to fall. That, of course, would be the force of gravity. The gravity of Earth is pulling this computer down towards its center. So there's really the only force acting on the computer if we ignore any air resistance. The question is, what would be the third law pair to this? If we know that the force of gravity from the Earth is pulling the computer down, what would be that match? Because again, every force has an equal and opposite reaction. Every force comes in pairs. So if we look at the relationships that we've seen in each of these examples, we basically said hammer pushes on nail, nail pushes back on hammer. Computer pushes on desk, desk pushes back on computer. In this case, Earth pulls down on computer, computer pulls up on Earth. Remember, gravitational pulls are always an interaction between two masses. In fact, when we get to some later chapters, we'll find that that force of gravity can be defined as a gravitational constant multiplied by the masses of the two things that are interacting and then divided by the distance between those two interacting objects squared. So any two objects that have mass can pull on each other with a gravitational pull. In fact, if you and your partner at school were sitting next to each other in your desks, there would be a gravitational pull between the two of you. As you maybe sit in front of your computer, there's a gravitational pull between you and your computer. Mass of you, mass of your computer, those two masses are pulling on each other. Because those two masses are small, you certainly don't recognize any force or acceleration of you towards your computer, but that force is nonetheless there. In this case, the Earth, being a very large mass, is going to pull down on the computer and have that gravitational pull. And the computer will go through a very large acceleration, since that force is equal to an ma. And the mass of the computer is very, very small. So its acceleration is going to be really big towards the center of Earth. On the other hand, we know that that third law pair exists between the computer and the Earth, and the computer's mass is also pulling up on the Earth. Basically, they're pulling towards each other. Now, when we look at the F equals ma for the Earth, the forces are exactly the same. Computer pulls up on the Earth, Earth pulls down on the computer. But because the mass of the Earth is so incredibly gigantic, the acceleration that we see for the Earth resulting here is going to be a very, very small acceleration. So the forces that each one experiences is the same. Same force on the computer, same force on the Earth. But because of their differing masses, the accelerations of each object are going to be very different. We'll look at some more examples when you come back to class and discuss any questions that you might have.